On this problem, we have the function y equals 4 square root of x, and we're supposed to find the change in y, delta y, that's called, that triangle is called delta to Greek D, uppercase D, when x is 5 and delta x is 0.1, and then find the differential dy when x is 5 and dx is 0.1. Okay, what are we talking about? Let me help you. Let me show you a picture. So the original function y equals 4 square root of x is here. So, with the 4 square root of x, that's the original function in red there. And the blue is the tangent, which we're going to find in a minute. Let me just tell you what it is right now. Well, I know what it is. It is, you know, yeah, the equation is y equals 2 over the square root of x. The square root of 2 over the square root of 5x plus 2 root 5. I'll show you how we find that in a minute. But the point is that they're very close. And at 5, they at 5, 5, is that where they yeah, at 5, right? Yeah, at 5. So at 5, they intersect exactly right here at over 5 up whatever. That's where they intersect. So you know what a tangent line is, right? It's a line that barely nicks the curve at only one point, and you can see it keeps on going here, and then over here it's getting the blue line's getting above the red again. So the original curve is the red, it's curved, 4 root, it's a square root graph, got curvature to it. A tangent line is a line that barely nicks a curve in just one point. So around here, they're very close. You can't even tell them apart. The blue and the red are so darn close. They're basically the same thing. So in higher math and science, we use tangent lines as approximations to an original, more complex curve because tangent line equations are easy. They're just x to the first power. Computer software can handle them better than original functions, which are more difficult, and they're about the same thing. So anyway, so on this problem, they're talking about the difference between delta x and dx. So let me help. So delta x and dx on this. And let's go back. They want the change in y at x equals 5. So first off, let's let's say so x is 5 here. And this little triangle is a Greek D. It's called delta. And just think D. It's a Greek D, and the D stands for difference. We use it all the time in math and science. That's an important thing to know when you see that D. This is the same thing. This is also a D. That's an English D, obviously. And here's a Greek D. Even though it's a triangle, I know, but it's technically a Greek D called delta. And it stands for difference. So that means the difference in x is 0.1. So that means we're going from so x1 is 5, x2 is going to be 5 add 0.1. In other words, x2 is 5.1 because the difference is zero point 0.1. It's zero point 0.1 further to the right. So we're going from x is 5 to x is 5.1, a difference of 0.1. And we're wondering when you do that difference from this x1 to this x2, what's the change in y? Again, that triangle means it's a D, difference. So whenever you see it in math or science, you want to think difference in y. What's the difference in y? Well, we could find that out, right? Here's y right up here. So we could say, well, y1 is going to be, plug into this function here, 4 square root of 5 when you put in x1. So there's y1, just plug in x1. And then what's y2? Y2, same function this time, plug in x2. So there's so the difference in y is they're saying find the change in y. So how much does y change from 4 root 5 to 4 root 5.1? Well, we can just subtract them. 4 root 5.1 minus 4 root 5. Let's go hit the buttons on our calculator. 4 root 5.1, oops, minus 4 root 5. So there's the difference, 0.0889999. They want to, there it is. See the answer? That's how we got that first off. That's all that's happening there. So again, that first part is saying find the change in y, delta y, the difference in y, when you go from x is 5 to zero point 0.1 further. A difference in x, 0.1 goes from 5 to 5.1. So you plug in 5 to the original function, it's 4 root 5. Then you plug in 5.1 to the original function, and you just subtract those, and you get that difference. Now, what's going on in part 2? Now they want the differential dy when x is 5. So again, we're going to have x1 is 5. Well, let's just start here. So let's take the function. This function right here, y equals 4 root x, and I'm going to rewrite that as 4x to the half because I want to find dy. How am I going to find dy? Well, we got to take the derivative. Dy dx, which is derivative, bring down the half. If you want, you can just make that 0.5 or half, whatever. 4 times 0.5, half of 4, 2. Subtract 1 here, minus 0.5. So I did the derivative, but we're wanting to find dy. So multiply both sides by dx. Those cancel. So then dy is 2x to the minus 0.5 times dx. So dy is 2. What is x? X is 5. We'll plug in that 5 there. 5 to the minus 0.5 times dx. Dx is 0.1. Let's go hit the buttons on the calculator. 2 times 5 to the minus 0.5. 2 times 5 to the minus 0.5. 2 times 5 to the minus 0.5. And times 0.1, is that right? Times 0.1. Times 0.0894427, 0.0894427, 0.0894427. There it is. 0.089442719. A lot of decimals there. Okay, now, so there's our two answers. So it wasn't too bad doing that. What is it we really did? So again, one more time, we found that the delta y, which is the change in y, the difference in y, from x is 5 and then to 5.1 because the difference in x is 0.1. And so what we did is we took the first x value and plugged it into the function, 4 root 5, took the second x value, 5.1, and plugged it into the function, then just subtract the y values, because y, and we got our answer. And the second time, for dy, that's derivative talk. So we took the derivative, and then we multiplied both sides by dx, plugged everything in. Now let me show you graphically what we just did. Now, we can't see it over here at 5 because they're so darn close. Well, I mean, we were at 5 and 5.1. They're just so close. But let me just show you somewhere more simple. Like if I was just to go um, if I was to go right here, say I was to go from here to here, there's a difference in y values, right? This, between this height, so there, that would be delta y. It's y2 minus y1. It's the difference in heights from this point. Now, I didn't really go from 1 to 2. We actually went from 5 to 5.1, but it's just too small to see anything on my graph. So imagine we went from 1 to 2 instead. There would be a delta y, the difference in y values. Okay, and in that same range, there would be a difference in these values, these heights, right? And so if I took this right here, This gap right here would be called dy. It's the difference in heights from the tangent line equation because the dy is all about the derivative. The derivative is the tangent line. So, no, how I found this, don't worry about it. You don't need it. But anyway, I wanted to show you what a dy actually is and what a delta y actually is. A dy is the difference in heights. It's how much, the tangent line goes up, and the delta y is how much the actual curve goes up between two values. That's what it is. So dy again is how much the dy is how much tangent line rises between the x values, and delta y is how much the actual function rises, the original, I should say. The original function rises. So we're saying, how much does the original from 1 to 2, how much does the red original function rise? And from 1 to 2, how much that's dy is how much the tangent line rises. That's what we just figured out between those points. We found dy and we found delta y. And by the way, notice they're very, very close. And that's the point. Tangent line's activity is very close to the original function's activity. And so there we go.